All right. Hello. Go ahead and started with some use substitution today. Sorry, let me get rid of this. And pop this on. All right. Sorry. So I like just finished with the exams. I still need to put the scores up. But they're all graded, so as soon as class is over here. Sorry, my nose is all itchy. As soon as we're done with class here, I'm going to post those. So you should know those before too long now. Sorry, I didn't quite finish in time to put the scores online. But I think it went pretty well, actually. I need to total the scores. The roughest problem on the exam was by a wide margin, I think the L'Hopital's rule won. People were forgetting to change it to the proper form to use L'Hopital's. You can't just swap the function for the derivative. You have to rewrite the function so that it's a fraction, and then you differentiate the top and the bottom separately. People were instead just taking the derivative of the function. But other than that, there was no sort of like problem that went seriously wrong, I think. And not even that problem went seriously wrong. People still kind of got some distance on that one. But anyway, I need to clean off this screen at some point. In fact, let me just do that right now. But anyway, so today we're going to do examples of use substitution, right, which is one of the key techniques for doing integration. Right, so this is a technique for basically undoing the chain rule. Right, and then the lectures for Monday will focus on the what's called integration by parts, which is a way to undo the product rule. Yeah, it was a little dirty. Okay, sorry about that. All right. So let's look at some integrals here. So I just have a list. The problem set for today is just a long list of integrals. So hopefully we can get through them all here. All right, so I'm just going to go down the list. Let me know at any point if you have questions. Anyway, let's go ahead and get started. So cosine of 2x dx. All right, this here. So again, whenever we're doing use substitution problems like this, or substitution rule problems, what we're basically trying to do is we're trying to imagine the thing we're trying to integrate has a piece that's a composition of two things. In this case, the only function here is a composition. We have cosine on the outside, 2x on the inside. And we're always going to make u equal to the inside of that. And then we differentiate this, so du is going to be 2 dx. So instead of writing du over dx, we're leaving the dx on this side. And the reason for that is we need a way to swap this dx for a du. Right? So I'm matching the stuff here up here. The 2x is here. Dx is here. So since we only have dx, we have to move this 2 over. We have to get 1/2 du equals dx here. And then we can just pop everything in for the integral. This integral becomes cosine of u. Dx turns into 1/2 du. All right, so we're just going to put that 1/2 on the outside here. You can leave it on the inside. It's actually not a big deal if you do. But I think it's always nice to pull out those constants if you can. All right, and now we're just integrating cosine, which is sine. So 1/2 sine of u, and then plus c. Right. And again, you know, the 1/2 technically distributes onto that c as well, but a half of an arbitrary constant is still just an arbitrary constant. So there's no real reason to worry about it. All right. So let's go ahead and replace the u with the original function for x. 1/2 sine of 2x plus c. And that's it. So a nice simple one to start off with. Any questions about that? Because once we have the basics of this, the rest of it aren't that bad. All right, so let's go ahead and do the next problem. Next problem is sine squared theta cosine theta d theta. All right. This one here looks spookier than it actually is. So when we're doing this, we want to think of, well, where is there a composition here? Right? So you might see it already. If you don't, what we can do is this here is sine squared theta, which is quantity sine of theta squared. So it might make more sense as a composition if we write it like this. Right? And then if we write it this way, you know, we can see here that, well, maybe this right here, the sine of theta itself, that's an inside piece, right? Sorry about that. All right. So a good thing to make sure of is if anything you're going to call, you know, u, make your substitution. Sorry, one more time. All right, I don't know where all that came from. Anyway, anything you're going to make your inside piece, anything you're going to call u, you do want to kind of make sure that the derivative of it is somewhere out here, right? And it doesn't have to be exactly the derivative, right? You can be off by a constant or something like that, and you'd be fine. But here, derivative of sine is cosine. There's a cosine out here, which is good. So u is sine of theta. Du is going to be cosine of theta, d theta. Now, let me say, you know, even if you're not sure whether what you're doing is going to work, you can always just pop the u in here. You could just solve for d theta here explicitly and see if things cancel out. And at the end of the day, your goal is really to just swap everything from whatever your original variable was to whatever you're calling your substitution. Usually we call it u, but it doesn't really matter what you call it as long as it's not like d or theta or anyway. So let's go ahead and swap our pieces out. Cosine theta d theta is exactly here. So here we have u squared u. That's 1/3 cubed plus c, which is 1/3 sine of theta cubed plus c. And there we go. That's all there is to it. So hopefully that's not too bad. I'm going to raise this chair a little bit. That's better. All right. Now my camera's all like super high. All right. So now that we got number 2, let's go ahead and look at the next problem. Number 3. I hope we don't get through these too quickly. X cubed over x to the 4th minus 5 dx. So here, we can use that same logic and try and see this function, see if there's a composition somewhere. Another way, at least I like to think about u substitutions, is there a part of this function which is sort of really inconvenient, which is really hard to use? And that turns out here, like if we look at the bottom of this, if the, say, x to the 4th minus 5 were on top and the x cubed were on bottom, we wouldn't really have any issue. Or even if it were like just x to the 4th on bottom and x cubed minus 5 on top, we wouldn't really have much of an issue because we could just divide it out. The problem is when we have multiple terms like this on the bottom, you know, there's not a good way to really do anything here. So what we can do, actually, is just take this whole bottom, because that's kind of inconvenient, and try that as a substitution. Now again, if you want to see if your substitution's actually going to work, it's not a bad idea to sort of see if you can find the derivative somewhere. All right, so here, u equals x to the 4th minus 5, du, or x cubed dx. So here, this x cubed dx part is right here, which is nice. So I do have to get this 4 out of here. That's fine. Then this integral here will turn into, keep in mind, we got that there. We got 1 over u times 1/4 d. I think we did an example similar to this in the lecture videos. Anyway, this is 1/4 integral 1 over u du. So we get 1/4. Remember, integral of 1 over u, the antiderivative of that, is ln absolute value of u plus c. Okay. So with that, now we're just going to plug the expression for u back in. 1/4 ln absolute value x to the 4th minus 5 plus c. And there we go. Any questions so far? All right. I lost a window. Actually, let me read this real quick. This is kind of relevant here. Awesome. So it looks like our TA might actually be able to do some remote hours, which would be great. So I'll talk with her, set up some time. Looks like she can do Tuesday or Thursday. So I'll set that up. Get that information, guys, as soon as I can. I saw that email and I was like, oh, that's something I've been waiting to hear. All right. Okay. Great news. So let's keep moving on here with some more of these integrals. So problem 4. Problem 4 is integrate x 1 minus x squared. X. Right, so there's a lot of basic examples here that are kind of similar to each other. So I'll let you guys think for a second what a good choice for u would be for this problem. A good choice for u, what would then be d? So hopefully your guess for what u should be here is the piece under the square root. Minus x. Then du is going to be minus 2x dx. And again, here we have an x dx. Here is x times dx. So sometimes, you just want to keep an eye out here. The pieces that you want to use aren't always right next to each other, so you might have to do some rearranging. Like, for example, maybe before doing the substitution here, we could rewrite this like this, and then here it'll make more sense. Here's the piece for u. Here's the piece for our du. Right, so just as before, we need to get that negative 2 out of there. And so this turns into square root of u times minus 1/2 u. That's minus 1/2 integral. I'm going to change u to u to the 1/2. Easy. Okay, so that's negative 1/2 u to the 3/2 over 3/2 plus c. All right, now let's simplify what we can here. This 1/2 out here and this 3/2 down below turn into minus 1/3 u to the 3/2 plus c. And now swap everything back over to x. Minus 1/3, 1 minus x squared to the 3/2 power, c, plus. That. Any questions there? Go ahead and move on to the next one then. Now the next one here is a little more interesting of an example. This one's a little more interesting than the last one. And that's because, well, think about what makes sense for you here. Think about that for a moment. And then think about what makes sense to choose as you. And then think about, well, what kind of changes that lead to. How can we deal with the rest of the problem? Think about that for a second. All right. So in this problem, the thing that most makes sense to be u is this stuff under the square root, right? Because that's kind of a problem down there. So we're going to make that equal to u. The problem is du is just 2 dx. So we got the dx, but what do we do about this? What do we do about this x here? How can we deal with that? Any suggestions how we could do that? I'm going to turn off the camera again. All right. So it kind of goes along the same lines of how we've been dealing with these extra constants in front of the dx. Right, so here, we only have dx, so we have to get this 2 out of there. But here I have an extra x that I need to turn into u's. Well, I can take my expression for u here and solve it for x. So that's going to be x equals 1/2 of u plus 1, right, to solve that for x. And now I can take that and plug it in here. So I get a 1/2 of u plus 1, get a square root of u, and I get a 1/2 du. Right? So now everything's in terms of u, which is what I wanted. So let's kind of multiply all this out, expand it, factor out constants. And if we do that, we get this 1/2 and this 1/2 both come out. Give me a 1/4. Integral. Here I have u times square root of u. That's u to the 3/2 power. And then 1 times square root of u. That's u to the 1/2 power. So I quite like problems like this because you have to think about, well, just how can we use this substitution, right? So yeah, we normally pick u based on wanting to simplify some certain part of it, but we can also use that substitution to pick away at other pieces as well. And that's what we're doing here. So let's go ahead and integrate this. 1/4. This here is going to be 2/5 x to the 5/2. This here is going to be 2/3 x to the 3/2. Oh, sorry, these are u's, not x's. U plus c. Okay. And then, so we'll distribute in this 1/4, and let's also replace u with 2x minus 1 again. So distribute that. This will be 1/10, 2x minus 1, 5/2, plus 1/6, 2x minus 1 to the 3/2, plus c. There we go. So the answer, interestingly, becomes quite complicated compared to the original answer here. But, it happens. Not that bad. If we factor out this part here, the 2x minus 1 to the 3/2, if we factor that out, we'll get a bit of simplification, but no real need to do that. Any questions here? Awesome. All right. So let's look at problem 6. So this is cotangent, integral of cotangent of x dx. Okay. So when we integrate this here, it's going to go similar to how the integral of tangent went. Right, so we integrated tangent in the lecture videos. Let's look at how we integrate cotangent. This one's actually a little bit nicer. Right, cotangent is cosine or sine dx. Right, And here, the problem is that sign on the bottom. So we're going to say u is sine of x, sine of d for some. Du is cosine of x dx. Okay. So here's our du. U is on the bottom. So we wind up with 1 over u du. That's it. So that's ln, absolute value of u plus c. And then we swap u back in. We have ln of sine of x plus c. Right. Now that is sort of the better form of the answer, or the nice form of the answer, the better form of the answer. I will say it's quite common to see this written in a different way. So if you remember, for integral of tangent of x dx, we got something like negative ln cosine x plus c. And we put that negative sign in there to write it like this. Right, you'll often get something like this. Or this is usually how you'll see this presented. Right? Even though this one's probably the nicer, more familiar way to look at it. Over here, kind of interestingly, even though this is kind of the prettier form of the answer, you'll often see people write a negative out here and then change this to cosecant on the inside. Right? Because we're sort of like putting a negative out here and then adding an extra negative power on the inside here. And the reason that's done is trig functions and their coversions, if you remember, we always swapped trig functions for their coversions or vice versa when we're doing the derivatives of all the trig functions. So like, derivative of tangent was secant squared, derivative of cotangent was negative cosecant squared. It's kind of meant to keep that that analogy there. So here, integral of tangent is ln of secant. Integral of cotangent would be negative ln of cosecant. Right? So even though these are sort of the better form, usually you're going to see them like this. Right? But of course, either way is perfectly fine. These are both perfectly valid answers. Use whichever one you want. And truth be told, I quite like the top one better here. I quite like this one better here. But again, do whichever form sort of feels better. Any question about that? Okay. So let's look at this next one. Number 7. We're going to integrate from 0 to 1 of 3t minus 1 to the 50th power dt. And I realize I've made a really dumb mistake. Awful. I have to compute 2 to a really high power. Or we'll leave it as an exponent, it's fine. So here, when we're deciding on what to make u, we actually just completely ignore the bounds. Those don't matter when we're trying to figure out what u is. And in this case, the thing that makes sense to be u is the stuff inside this power. Now, theoretically, we could expand this out, but that would be pretty horrible. So the better way is to do this with a u substitution. Du is going to be 3 dt. So when we're plugging these things back in, or plugging these things in, it will be u to the 50th. And dt will be 1/3. Now these bounds, I take 0 and I plug it in here. So u of 0 is 0 minus 1. Bottom bound is -1. U of 1 is 3 minus 1, which is 2. Here. So let's do this integral. We're going to get 1/3 times 1 over 51, u to the 51, and we evaluate this from -1 to 2. Okay. So when we evaluate this, see, we're going to have 1 over 153 here times, now 2 to the 51st power, that's some really, really large number. So I'm just going to leave that as 2 to the 51. No reason to try and expand that. That has probably at least dozens of digits, I'm going to guess. Now, -1 to the 51st power, actually, we can compute. It's an odd power of -1, so it's going to be negative. So if you really want, we can write this like 2 to the 51st plus 1 over 150. Okay. And again, it's not so important what that number is, but go about it. Questions here. Okay. Let's look at problem 8. So problem 8, we're integrating from 0 to 1, x e to the minus x squared dx. Okay. So when doing this one, well, we're going to figure out, well, what part looks like a composition, what part looks hard to deal with, and it's that x squared in the exponent here. So u is -x squared. So du is going to be -2x dx. Okay. So with that, let's start plugging that stuff in. So again, don't worry about the bounds just yet. Here we have x dx. So this part will be our e to the u. The rest of this has to be -1/2 du. And then we need to sort out our bounds. So u of, should do these in the right order. U of the top bound is -1. U of the bottom bound is 0. So this just swaps to 0 to -1. Okay, so let's integrate this. -1/2. Integral of e to the u is e to the u. And then we're evaluating from 0 to -1. So this is -1/2 e to the -1 minus e to the 0. And really, you could stop there. Like, this is fine. If you're really interested in sort of making things look nicer, you could write this as 1/2 of 1 minus e to the -1. But I think this is a perfectly fine place to stop. Any questions here at all? All right, cool. So let's go ahead and the next piece, 9. 9 is going to be from 0 to 3. dx over 5x plus 1. So again, this is basically, I don't think I've written it like this. Normally, I don't like writing dx on top, but I did it because I wanted to make the point that this is really this integral right here. We're really integrating that. Right, so if you see dx on top, that's just 1 times d. So here we're going to make u be 5x plus 1. And du will then be 5 dx. Right? So we want to substitute this stuff in, as usual. So here, we'll get 1 over u dx turns into 1/5 du. Now what do the bounds become? Plug 0 in here. Let's plug in 3 first. So u of 3 is going to be 5 times 3 plus 1, 16. U of 0 is 0 plus 1, which is... Integrate this. So we're going to have 1/5 ln, absolute value of u, and this whole thing is from 1 to 16. So we get 1/5 ln, absolute value of 16 is just 16, minus 1/5 ln, absolute value of 1 is 1. ln of 1 is just 0. So you could say 1/5 ln of 16. Good to go. Right, you can make that, ln of the 5th root of 16 if you were so inclined. Don't feel like you need to do that. Any questions on that one? Let's go on to number 10 here. Number 10, now this one is a more interesting problem, I think. In this one, we really need to think about where we want to make the substitution. So I'm going to leave this here for a second. Think about what you would make the substitution. Try and work it out, and then I'll work it out. See if we get the same thing. Have a go at that one. So let's go ahead and work through this one and see how it went. So here, we have kind of two parts that seem decent candidates. We have the x squared on the bottom, but really, at the end of the day, the biggest thing we want to look for when making substitutions is something that looks like a composition. That would be the top here. Right? So e to the 1 over x is the composition part. So we're going to choose u to be the inside of that composition, 1 over x, du. Oh, sorry, I wanted to write du underneath it. Du is negative 1 over x squared dx. Okay. So notice that x squared and that dx is this right here. Is there? All right, so let's see. U of the top is 1/2. U of the bottom is 1. So let's go ahead and plug all that in. So this goes from 1 to 1/2. And this is just e to the u times negative du. So when we integrate this, we have e to the u from 1 to 1/2. So it's negative e to the 1/2 minus negative e to the 1. And if you want to make this look a little bit better, this is 1 minus square root of e. They are. So, any questions there? That all look good? All right, then. Well, I have one more question today. This is number 11. Integral of secant of x dx. Now this one's a bit weird. Because, okay, secant is 1 over cosine. But even if we do this, there's not really a way to deal with this, right? This still doesn't get us anywhere, which is a bit unfortunate. But it's fine, because we're actually going to use a weird trick on this one. Now, the trick for this seems kind of out of the blue, and in ways it is. There's actually a better way to do this particular problem, but we need something called partial fractions. Sorry about that. All right, so the way we do this secant of x, I'm going to multiply this by something a bit odd. Right? I'm going to multiply it by secant x plus tangent x over secant x plus tangent x. Now you might wonder, well, why would we possibly want to do that? Well, the reason is, let's look at what the top is. Secant squared x plus secant x tangent x. And let's look at what the bottom is. It's going to be secant of x plus tangent of x dx. So this piece has a derivative right here. This piece has a derivative right here. So what we're kind of doing here, and secant is kind of unique in that this kind of trick works out, is what we're doing is we're creating something we can use as a substitution. So here, the substitution to pick is u equals secant x plus tangent x. Then du is going to be, well, let me write it in the right order for this. Secant x tangent x plus secant squared x dx. So what then happens here is this becomes an integral of 1 over u du. So it's a little bit tricky, that one. But this is how you can do this with u substitution. So we get ln of absolute value of u plus c. And so the final answer would be ln absolute value secant x plus tangent x plus c. And there you go. So a bit of an odd answer, right? But it actually works out pretty well. Any questions there? All right, well, we got a few minutes left here. Any questions at all anyone wants to ask? Just a reminder, I did put up on WebAssign kind of like a sample of what the segmented exam pieces will look like. So that's sort of what most of them will be. Awesome. I'm glad. This is one of the important tools here. So good to know how to do. Yeah, I'm trying to decide here if I want to do secant and the less spooky. Still a bit of a trick to do it, but it doesn't kind of require this. Well, I guess I'm never going to ask you guys to like recreate. Well, This would be hard to do on WebAssign anyway, but I'm never going to ask you guys to recreate this integral up in a table or something. I guess I'll say the way you would go about it in the non-spooky way. So you do want to look at it like this, but you actually change it up a little bit more, and we multiply by an extra cosine. This. And then on the bottom, we use the trig identity to swap this over to 1 minus sine squared. And then it becomes a u sub. Turns into integral 1 over 1 minus u squared. Oop du. I keep getting so many. But now this one, to integrate something like this is a technique we haven't talked about, but what we can end up doing is we can split this like this. I think the way this splits is 1/2 here and 1/2 here. So if you add these two fractions back together, you should get this. So there's a way to kind of do this. And at this point, these are just simple u sub integrals to do again. So I'll let you think about how the rest of that goes. You do have to do some clever work to get it back together into one piece like this, but it's not actually too bad at the end. But anyway, I will, I think I'll stop here. And glad this stuff makes sense. Hopefully anyone who's watching this later, hopefully this makes sense there as well. Yeah, take care. Have a good afternoon. And for the lab on Friday, I'll have something posted. I think I just want to go through like how do we integrate, how do we set up certain things like that. I don't think I want to do anything. But yeah. All right. But have a good afternoon.